So as usual, welcome to today's session of the course. What we are going to do today is to continue our study of languages, grammars to generate languages. And today we are going to add one more item to this study of languages, namely the introduction of some very simple machines that computer scientists have used for a long time, at least as far as computer science is concerned, to recognize languages. So as usual, before we start with any new material, let's warm up by trying to answer some questions from my alter ego, namely Dr. X. And these questions are here so that we can refresh our memory of what we were doing, and we can do some more exercises. So we don't just do exercises during the exercise session. There is really no difference between lectures, exercise sessions, or anything like that. They are just course sessions in which we work with the material. In some sessions, I speak more than you do. In some other sections, you just work and I'm not there. So here's a question for you from Dr. X. Dr. X was looking at our slides from our previous lecture, and he looked at this language. This is the language that consists of all the strings of A's and B's that start with some number of A's, possibly 0, followed by a B, followed by a number of A's. Note, the number of A's that follows the B should be exactly the same as the number of A's that precedes the B. Now, the claim that I made on my on the slides was that this language is a context-free language. Now, context-free languages are languages at the low level. They are not the lowest level, but at a low level of the Chomsky hierarchy. Can you help Dr. X figure out why this language is context-free? What does he need to do in order to convince himself that this language is context-free? I say himself because Dr. X is a man. Sorry, bad for him.
I at least noticed that any string generated by this is a palindrome.
Okay, what he said is, your colleague is saying, I noticed that any string generated by this is a palindrome. That's absolutely right. Any language actually in this language, so any string in this language is a palindrome. That's absolutely right. But why does it say that this language is context-free? When is a language context-free? Okay, so I don't expect you to remember things. So let's look at our visual memory here. Context-free languages are what, in a more boring way, are called type 2 languages. Now, sort of, this makes it look like we are doing blood types. Let's call them context-free. And the language is context-free when it can be generated by a grammar whose productions have a very specific form. And this form is exactly the one given here. Namely, on the left-hand side of the production, you have a single non-terminal. On the right-hand side, you can have any string of terminals and non-terminals. Okay, so in order to prove, if somebody asks you, like Dr. X, to prove that a language is context-free, all you need to do is to come up with a context-free grammar, that is to say, a grammar that has productions only of this type that generates the given language. If somebody instead asks you to prove that the language is regular, then what you need to do is to come up with a grammar whose productions have one of the given forms, or of this type, which are completely equivalent, that generates that language. Okay, in other words, context-free languages are a special class of languages. And the reason why they are special is that in generating them, you cannot use arbitrary productions. You have to use productions that are kosher, where kosher in this case means they have this form. You can imagine that if you try to write a production that is not of this form, then you get spanked by a compiler. Okay, but we are not doing caning here or anything like that. The compiler will complain and say, sorry, I'm not going to buy this production because it's not good. Okay? So now that we know what we have to do, you know what I'm about to say, I'm going to take out our scratch pad and I'm going to be your writing tool. So that's the language we want to generate. Okay, and as usual, I need to get used again to this different writing setting. Okay, I want a grammar. I want a grammar that generates strings in this language and only those. All of them and only those. Now, your colleague before actually had a very good observation. These strings are palindromes. And we saw last time how to generate palindromes over the binary alphabet. Perhaps we can massage what we did, change it a little bit to generate only palindromes of A's and B's of this form. So what is the shortest string in the language? That's our base case. Say it again. Okay. The shortest string, the suggestion is that it's the empty string, but look at this. Sort of, you can take 0 A's before and after the B, but you have to have a B in the middle. So the shortest string is B. So why don't we write a production that generates the shortest string? That's how we can get started, our recursive generation of strings. Okay, that's the first production. S is the start symbol. From the start symbol, we can immediately generate a B. Now, suppose somebody, Dr. X, gives you a string in this language. How can you make it longer? Absolutely. Your colleague here is saying by adding an A at the beginning and an A at the end. Because if somebody gives you a string in this language, then this string will have the form some number of A's, a B in the middle, and then some number of A's, which is of the same length as the one you had before. If you stick an A at the front and an A at the back, then you still have a string in the language that starts with n plus 1 A's, a B, and then n plus 1 A's. That's okay. So now, who generates strings in this language recursively? S. S is the guy. So I write another production that has an S in the middle, and recursively this will generate this thing here. And what do I put before and after the S? I put A's. Do we need any more productions? One of your colleagues already shook his head and said, no, we don't need anything else. Why? Because suppose that I want to generate this string here. This is the string W that I want to generate. How can I generate it? Well, first I want to get some number of A's at the beginning, the right number of A's at the start, the right number of A's at the end. And then I want to put a B in the middle. So what do? I repeatedly use this production to generate a string. So if I call this my production 2, P2, I repeatedly use n times the production P2 to generate what? If I use it n times, I will create n A's, then I have an S in the middle, and then I have n A's that follow. Now I want to put the B in the middle. I'm going to use the production 1, which is this one. I put the B in the middle using that production by rewriting the S in the middle with the B, and I'm done. The only thing that changes is how many times I repeat the use of production P2. The longer the string I want to generate, the more times I need to put A's at the beginning and at the end. Okay? Anything weird about this? Anything you don't understand? If so, scream now or forever rest in peace. No, we are not getting married here.
Right. So you just have the B in the first, and then you just add 2 A's, and then you check, and then you add 4 A's.
Yeah, your colleague is saying, okay, so the first production is to put the B in the middle, and the other production is to generate A's recursively as many times as you need. And then once you are satisfied with the number of A's you've generated at the beginning and at the end, you will put the B in the middle and you terminate. Absolutely. Okay, today Dr. X actually had the second question. And the second question also has to do with grammars. Now, this is, oh, by the way, here's a grammar which is substantially larger than what you will have to write down yourselves in this course. But here's a grammar. It's a grammar from the book, actually, from chapter 13 in the American edition of the book. I don't remember what page it is, but you can find it. It's in example 7, wherever example 7 is. Okay, so first question. Is this a context-free grammar? Your colleague is saying no. Why not? Absolutely right. Why not? Yeah, because there are productions which are not legal for context-free grammars. Like, look at this one. 1B is replaced by 1-2. Well, in a context-free grammar, what is on the left-hand side should always be a single non-terminal. This is a string. It's not a single non-terminal. It contains a terminal and a non-terminal. That's not allowed in a context-free grammar. It's allowed in a general grammar, a general phrase structure grammar, but not in a context-free grammar. Okay, excellent. Now, the claim in the textbook is that this grammar generates this language. Now, it's a claim in the textbook, but textbooks can be right and it can be wrong. Is this right? One of your colleagues is saying no. Why not? Okay, so there was a guess. Sorry. It doesn't happen. But you know, since there are lots of productions in here, and the language is fairly complicated, these productions are very complicated, I wouldn't ask this question if it wasn't easy to figure out that the answer is indeed, this is wrong. Okay, why is it easy? Now, look at this production here, okay? This production says S goes to the empty string, that's easy, that's no problem. The other one says, well, if you don't want to generate the empty string, the first thing you do is you rewrite S to a capital C. What is it that you can do afterwards?
Well, you can generate A1 and you use that to make the 0 CAB.
Okay, then you have to use the production for C. And the production for C says C goes to 0 CAB. And now what is it?
The problem is that you can generate A2 to the right of this and A1. Like the A can end up as A1 and the B can end up as A2, but the C can also end up as A1 and 2.
Okay, your colleague is giving an explanation, but there is a simpler one. You can never get rid of the C. There is no production that says, okay, C can disappear. It can turn into a terminal. So actually, you can never generate, apart from the empty string, you can never generate any other string that only consists of non-terminals. The only string that you can generate is the empty string. So not only this grammar is wrong, it is badly wrong, because it only generates one string, whereas it had to generate an infinite number of strings. It is a dysfunctional grammar, your colleague is saying. Now, I don't know. I mean, yeah, it doesn't work. It doesn't work. Okay, so on the slides for our previous lecture, you will find a correct grammar for generating this language, and you can work with it. At home, I would encourage you to think as to whether this grammar can be fixed in some way. We are not doing it now, but my message was you have to read critically, because even if the textbook says X, well, any author of a textbook, including me, especially me, in fact, can make mistakes. We are all human. So whatever I say, don't take it as if it has come from some gospel. I can make mistakes, and you have to think critically. Okay, that's the main message here, apart from the fact that you've been able to figure out why this doesn't work. You've done grammar debugging, because grammars need to be debugged just as programs need to be debugged. And thinking critically in grammar debugging will also help you when you write programs. Of course, your programs are immediately correct, aren't they? Of course, because you wrote them. But for people like me, most of the time they're actually wrong many, many times until they become correct, hopefully, at some point. So critical thinking does help in everything you do. Okay, so this was a message for your life more than for this course itself. Okay, excellent. Now that we have pleased Dr. X, let me give you a little bit of a closing, 2 slides, closing message regarding grammars, and then this will also tie in very nicely with our next topic. Now, there are really 2 very fundamental classes of languages for you. We've seen the Chomsky hierarchy, and at the Chomsky hierarchy, there are languages in the higher part of the egg and languages in the lower part of the egg. Now, they're all fundamental, these classes of languages, but 2 are more fundamental than others: the context-free languages and the regular languages. Why are they so fundamental? Context-free languages are fundamental because they are the kind of context-free grammars are fundamental because they are the grammars that people use to describe the syntax, the large part of the syntax of programming languages. Not all of the constraints of the syntax of a programming language can be described using a context-free grammar. For instance, using context-free grammars, you cannot make sure that variables are declared before they are used. That's a constraint that you have in many languages, but it cannot be described using a context-free grammar. But most of the syntax of a language is specified using such grammars. Why? Well, there are very good reasons. Inside any compiler that you use, there are machines that recognize context-free languages. Anytime you actually compile a program, there is a front end of the compiler that will look at the syntactic structure of your program, and based on the grammar that describes the legal programs, syntactically legal programs in your language, will generate an object called a parse tree that basically describes what the structure of your program is. I think that you did it before by hand when you were in Icelandic classes or whatever your natural language is. Why? Where you were given sentences in Icelandic and you had to divide them into subject, verb, object. Didn't you do this? In my time, this was called logical analysis in Italy. Boring as they get. Luckily, in computer science, you don't need to do this yourself. The compiler does it for you and produces this tree-like structure, which is called a parse tree. And it does so automatically by means of an algorithm that is generated from the grammar, provided the grammar is a context-free grammar. Isn't it beautiful? Isn't it useful? You don't need to work. The algorithms do it for you. And the thing is that once the compiler has in its hand the parse tree for your program, it can do type checking, code generation, anything it needs to do using recursive algorithms. We are not subjecting you to recursion because we are nasty bastards. That's because it's very useful. And this is an example in which recursion is extremely useful. So as Archimedes said at some point, give me a parse tree and I will lift the world. Well, he was not talking about parse tree, he was talking about levers, but in this case, the lever, not this, the lever, is actually something, the parse tree is the lever that the compiler uses to actually do everything it needs to do with your program and generate source code. So that's one of the reasons why context-free languages and grammars are fundamental. It's not the only one. Regular languages. Now, the parser that does actually the construction of the parse tree in your compiler relies on something which is called a lexical analyzer. The lexical analyzer looks at the string that your program is nothing but a long string, possibly longer sometimes than other times, but it's a string of symbols, and it breaks it up into its individual components. Is this a keyword of the language? Is this an identifier, a variable, a legal function name, a legal method name? Well, who does this job? And how are these legal syntactic components of your language described? Well, they are described using regular languages. That's a subclass of context-free languages where you can do pattern recognition very, very efficiently. In computer science, anytime you do pattern recognition, and you do it all the time, for instance, when you're doing a text search, you're using the fact, there are algorithms that are based on the fact that such patterns can be described using regular grammars. So for instance, the set of identifiers in any programming language is a regular language, which is generated by a regular grammar. For instance, how would you describe the set of identifiers in C++? What is it that you can use as variables?
Integers, like, there's so many types of it.
Oh, no, I mean, yeah, I mean, what names? What is a good name for a variable? Is 1, 2, 3 a good name for a C++ variable? No, it isn't, because it's not illegal. Is a 1, 2, 3 a good name for a variable? Yes, it is, because it starts with a letter. It doesn't start with a digit. Is 1, A23 a good name for a variable? I don't think so. So you see, there are a set of rules that tell you what the legal variables are. All the strings that match these rules form a regular language. And today, we will see many more examples of regular languages. Because for 2 or 3 lectures, we will only be looking at regular languages. Because regular languages are one of the most beautiful and most useful objects in computer science. And they have been since 1956 or thereabout. So they are not a new thing. They are something that has stood the test of time in computer science. You know, in computer science, 50 years is the eternity. Try to imagine computers 50 years ago. You can't. Unfortunately, I sort of can. This sort of indicates. So the closing message for the grammar and recursion part, sort of, is that recursion is your friend, is very powerful. You can use it to define languages. You can use it to define other objects in computer science. And once you've defined these things recursively, you can operate on them recursively, like your compiler does in the front end. So respect your compiler. It has recursion inside, not just Intel inside. Wonderful. So, well, I say wonderful because this stuff is really wonderful. I love it. And I hope it shows. But you will love it too. So where are we so far? We've seen that in computer science, we love languages. We use languages all the time. How do we describe what are the strings which are legal in the languages that we want to work with? We use grammars. Grammars are devices to generate languages. You use the productions, turn the crank, and out come legal strings in the language generated, described by that grammar. However, a program like a compiler, it does not generate programs for you. It doesn't. It would be nice if it did. Hey, compiler, give me a program to solve this assignment. Cool. Perhaps one day this will happen with the advances in AI, but not quite. We are not quite there yet. What the compiler does, it takes a program as input, it recognizes it, it says whether it's legal or not, and then if it's legal, it will generate target code so that it becomes executable for you and do other stuff. Perhaps optimizations that you would never have dreamed of doing. So the compiler is in some sense a machine that recognizes input strings. It does not generate them, it recognizes them. And this is something that pervades computer science all over the place. We have languages that we want to accept, to recognize, not just to generate, and we want to have machines that generate them. Now, whenever we want to achieve a task, we want to use exactly the right amount of resources that are needed to carry out the task that we want to generate. So a natural question for any computer scientist is, given that this is the collection of languages that I want to handle with my program, what is the simplest machine that recognizes them all, and only those? For instance, if I'm only interested in regular languages, what is the simplest machine that recognizes regular languages and only those? Simple is beautiful. The KISS method.
Keep it simple, stupid.
Absolutely. Your colleague said, keep it simple, stupid. I always like to omit stupid and change it with Sigurdur, Sigurjón, whatever name that starts with an S. Because stupid, no one else here, no one here is stupid. In fact, there are no stupid people in the world. Well, actually, I'll take it back. There are. Many of them become Italian prime ministers at some point. Unfortunately, not only in Italy. I think you can, so sorry, I'll stop here because then I get into trouble. And they might be listening on YouTube. Okay, so now you might say, well, I mean, this must be a very complicated machine to recognize regular languages. But in fact, the beauty of it all is that to recognize regular languages, we need a machine, which is essentially a programming model that you can learn in 1 minute. Or perhaps I'm slightly exaggerating, perhaps 2 minutes. It's a very simple programming model. And it's a model that some of you have already used in the problem-solving course. But if you haven't used it, it doesn't really matter. You can learn it in 1 minute. So let's try to have a mental experiment here. Suppose that we want to come up with a device that recognizes the language that consists of all the bit strings that start with a 0. Okay, this is a computational device, it's a machine, so it will have an interface. And the interface is the collection of input symbols that it's willing to process. In this case, it's bits. If it was ASCII symbols, the machine would be different. But in this case, we know we are going to feed this machine only with strings of bits that start with a 0. Since we want to recognize strings, and we want to figure out whether these strings belong to the language that we want to recognize or not, the natural thing is to say that the machine reads the input string 1 symbol at a time. And as it reads the input symbol, it will make some decision in order to remember whether what it has seen so far, and remember some interesting information about what it has seen so far. Is it good? Is it bad? Now, when the machine has read the whole input string, it will decide whether what it has read is good, it likes it, or not. It doesn't. And in that case, it will give a Boolean output. It will say, yes, I'm happy. The string you gave me as input is a good one. No, I'm unhappy. You fed me with junk. Well, at least as far as this language is concerned. Shall we program such an automaton so that you can also see what such an automaton looks like? Everybody's screaming, yes! So let's do it. Okay, remember, we are interested in a machine that accepts all the strings of bits that start with a 0. So the language that we are interested in is all the strings of bit that start with a 0. So it's all the strings that are of the form 0W, where W is any string of bits. And remember, the set of all strings of bits is 0, 1 star. Okay? So my machine at the interface will look like as follows. It will take as input a string, and the output will be yes. So if we call this language L, it will have to be yes, W is in L, or no, W is not in L. So this is the Boolean output I was talking about. Now, let's assume that this machine has some states, and in particular, we start processing its input string from an initial state. When I draw a picture, this initial state will be depicted with an incoming arrow from nowhere. Okay, now the machine starts reading bits. The first bit in the string that it reads is either a 0 or a 1. If it reads a 1, what does it do? It will have to remember that the string is good or bad. So it's supposed to be happy only when it receives as input a string that starts with a 0. So if the input string starts with a 1, should it be happy or not? No, it should not be happy. So it will remember that it's not happy by going to a state where it's not happy. And I mean, if the string starts with a 1, does it matter what comes afterwards? No, you are happy and you will remain, so you're unhappy and you will remain unhappy forever. Absolutely. So from now on, the machine will have to be happy. We'll have to accept any amount of input that it gets, but no matter how many zeros and ones it gets, it stays unhappy. You have to loop. Well, the question is, do you have to put the loop? Yes. In this programming model that I'm defining today, you have to put the loop. We will see later on a slight variation on it where you don't have to put the loop. But anyway, the message is, if you're unhappy, you will remain at the beginning, you will stay unhappy forever. Okay, what's the other possibility? The other possibility is that you see a 0 to begin with. Well, once you see a 0, you're happy. Why? Because you've seen the only thing that you wanted to see. Anything that comes afterwards, you don't care. You're a happy-go-lucky person in this case. The only thing that you wanted to check was, does my input start with a 0? If yes, then anything follows, anything goes. So how do we say anything goes? We just stay in the same state, no matter what follows the initial 0. Okay? So this is a finite automaton that recognizes this language. Why does it recognize this language? Because when it processes a string in L, it will always land on the smiley. That's the happy state. These are formally not written as smileys. They are written with a double circle, and they are called the accept or final states. If instead it gets fed with a string that starts with a 1, these are all the strings which are not in L. Oh, just a second. There is another one which is not in L, but that's the second. So if it gets fed with a string that is that starts with a 1, then it will not accept it. Why? Because it will land into the unhappy phase, which is not an accept or final state. There is one more string, and that's the empty string. If the machine starts in this state and it reads no input symbol, it stays there. So this is also an unhappy state. We have not marked it with a smiley. Okay, so the machine only changes state by looking at the next input symbol. Okay, that's an informal explanation of what a finite automaton is and how it operates. Let's do another example. I'm going to make you work a lot today, even more than usual. So there you are. There are actually 3 questions here. We're probably not going to do them all right now, but let's look at the first one. This is again a language over the collection of bits, and it consists of all the bit strings that start with some number of zeros, possibly no zero at all, because M can be 0, followed by some number of ones. And there is no relationship whatsoever between the number of zeros and the number of ones. And the number of zeros and the number of ones can be none. So what is the shortest string in this language? The empty string. You write no zeros followed by no ones. Okay, so what I want you to come up with is a finite automaton that accepts strings of this form for me. Huh? Now, you might recall a similar language to this one at the end of our previous lecture. The only difference was that instead of zeros and 1, I had written A's and B's. And this is also posted as an extra question on Piazza for those of you who would like to try. So let's not spare this virtual paper. That's a language I want you to come up to. I want a finite automaton for. Okay, so I'll do the easy part. I'll draw the start state. Now, remember, if I get the input string, I'm this machine, I get the input string, which is empty, then I stay where I am. Since lambda, the empty string, is in the language that I want to recognize, what kind of state should the start state be? Should it be a happy one, an accept one? It should be a happy one. Why? Because if I get fed with the input, the empty input, I stay there. And then I ask myself, well, I finished reading my input. There was no character in the input. Am I happy? I look at the nature of the state where I am. And if it's a happy state, I say, yes, I accept. Otherwise, I say, no, I reject. In this case, I want to accept the empty string. So this is a happy state. I'll denote it by a double circle instead of a smiley, even though the smileys are nicer. Huh? Okay, what next? What is it that can come next? A 0 or a 1. Okay, so let's assume that I see a 0. Now I have a decision to make. Do I go to a new state or do I stay where I am? Okay, so there are different possibilities here, sort of different suggestions. One of your colleagues is saying, let's loop with 0. So let's try this. Now, whenever you do these kind of things, I encourage you to try and write down what the meaning, the intuitive meaning of the state is. In this case, I would say that since we are looping back on this state by seeing zeros, the meaning of this state is I've seen some number of zeros. 0 or more zeros, but I haven't seen any 1 yet. So this state really represents I have seen only zeros. Okay, since this state means I have seen only zeros, if I see a 1, I better change state. Because if I see a 1, I haven't seen only zeros so far. Oh, lovely. Okay, now I go to a new state. What kind of state is this? Should it be an accept state or not? One of your colleagues is saying, yes, it should be an accept state, and it has to be. Why? Because I can reach it by seeing any number of zeros followed by a 1. And any number of zeros followed by a 1 is legal. So this should be an accept state. Excellent. Now, I'm in this state. What can I see next? I can see a 1 or a 0. If I see a 1, where do I go? Your colleagues are saying I should loop. Why? This makes sense because this state actually intuitively means I have seen some zeros followed by some ones. I have seen a string of the form m zeros followed by n ones, which are the strings that I'm interested in. But what if I see a 0 now? Yeah, now we become unhappy. Why? Because if I see a 0, and let's change the color, this becomes red because it's bad. I don't know why red is bad. But anyway, sort of, it's an error. Anyway, I think from elementary school, we get used to errors being marked by red things for some reason. Yeah, it's the color of blood. But I mean, fortunately, blood is not, is good. It's not bad. We wouldn't live without it. Yeah, fire, whatever. Anyway, the important thing is that now we are really unhappy. And why are we unhappy? Because we've seen a 1 followed by a 0, which is not okay. And once we are unhappy, do we change our mind? No, once we are unhappy, we stay unhappy. Bingo, that's a finite automaton that accepts this language. Now, how do we figure out whether, yes, question? Yeah. Okay. Your colleague is saying in the description you say, I have seen some zeros followed by some ones, but in fact it could be 0 zeros. But 0 zeros is some zeros, namely none. So you see this is for some number of zeros. And it could be absolutely right. But if I'm here, I know for sure that I have seen at least 1. That's the only thing I know. And that before I've only seen zeros. Absolutely. Excellent point. Question. Okay. So so your colleague is saying, well, could I have just come up with a different finite automaton, which makes a different decision in the start state? You would, instead of staying where it is when it sees a 0, it could go somewhere else in a new state, which is also an accept state. There are many different finite automata that accept the same language. So you can get an absolutely correct finite automaton that actually takes that decision. This one is the smallest finite automaton for this language. But there are many, many correct finite automata that accept all the same language. Excellent question. Another question before we break. The question is, should we always try to make it as simple as possible, the smallest that you can? I think it's very often the case that the simplest the solution, the easiest it is to figure out that it works. But unless I ask you, give me a finite automaton with 3 states that accepts this language, then any correct answer will be correct. And in fact, as you will see, it will not be me telling you that your answer is correct, but it will be a piece of software that you will interact with, which is called the automata tutor, that actually also tells you where you've gone wrong when your automaton doesn't work. And this piece of software will grade your next assignment automatically. And it will also tell you how much you get. Well, at the end of the day. Okay, let's have a break now. We've done a lot of programming. We'll do more programming after the break.